Today, the curious cameo of coenzyme A in the citric acid cycle explained.
Ketogenic diet has neurological benefits. Why do we have to eat such an enormous amount of food?
Complex science, clear explanations. Class is starting now.
Hi, I'm Dr. Chris Masterjohn of chrismasterjohnphd.com, and you're watching Masterclass with Masterjohn. Today we're in our 9th in our series of lessons on the system of energy metabolism. And we're going to talk about this curious fact that coenzyme A, having dropped the acetyl group off at the citric acid cycle to go and leave to pick up other acetyl groups, now all of a sudden, in the case of the alpha-ketoglutarate dehydrogenase reaction, comes back to form succinyl CoA, and then just leaves in the next step to form succinate. If the purpose of coenzyme A is to bring molecules to the citric acid cycle, why would it come back and then leave? And that's the puzzle that we're going to solve today by talking about the role of coenzyme A in carrying energy in the high-energy thioester bond. Now, recall back to the first lesson where we introduced the citric acid cycle, and we talked about the role of coenzyme A in preventing acetate from evaporating. That's very real because acetate is volatile, and if free acetate was a true metabolite in mainstream metabolism, the risk that it would volatilize would be very high. So the role of coenzyme A in weighing down the acetyl group to create a much larger molecule that's much less volatile is very real. But it can't really explain why we need succinyl CoA when we also have succinate, and that's not a problem. Succinate is much larger than acetate and correspondingly much less volatile. We have way larger molecules that bind to coenzyme A, like very long-chain fatty acids. So what we're going to see in this lesson is the principle that really applies across all metabolism for why we have coenzyme A. And it's all about the capture of energy. As summarized on the screen, a chemical bond is biologically useful for energy metabolism when it is kinetically stable but thermodynamically unstable. When we talk about kinetic stability, we're talking about, number one, the rate of a chemical reaction, and we're tying it to, number two, the activation energy. Something with a low activation energy is kinetically unstable. And correspondingly, or conversely, something with a high activation energy is kinetically stable. Well, what do we mean by that? When we talked about activation energy and enzymes, we noted that the rate of a chemical reaction is largely driven by the activation energy barrier. In fact, the way that enzymes speed up the rates of reactions is to lower the activation energy barrier. What that does is, within a given population of molecules, it lowers the barrier and thereby increases the proportion of those molecules that have the kinetic energy sufficient to react when they collide with one another. If you increase the proportion of molecules that are moving with sufficient energy by lowering the energy barrier, then you increase the likelihood that when any two molecules collide, they will have the energy that they need to get through the transition state and become the products. So kinetic stability is about activation energy, and it's about the speed of the reaction. By contrast, thermodynamic stability is about the delta G. Something with a negative delta G is thermodynamically unstable. By contrast, something with a positive delta G is thermodynamically stable. The delta G says nothing about the speed of the reaction. It's all about how favorable the reaction is. If something is energetically favorable but kinetically stable, then the end result is for lots of product to form, but it's going to happen very slowly. In biologically useful chemical bonds, what we want is a high activation energy barrier, but a negative delta G. That makes it kinetically stable and thermodynamically unstable. The kinetic stability means that it's easily controlled by enzymes, and the thermodynamic instability means that there's a high payload to being able to metabolize that bond. Now, recall that most things that happen in the body are very kinetically stable in the absence of enzymes. When we first talked about enzymes, we noted that the rule is that most reactions that happen in the body have activation energy barriers that are way above body heat. So body heat cannot provide the energy in the uncatalyzed reaction to get over that barrier. And the role of an enzyme is to bring the activation energy barrier below body heat. So unless otherwise noted, the rule is that all these things are kinetically stable. So it actually makes the difference when we're looking at the different advantages of different molecules in the body to use their bonds for energy metabolism is really all about the thermodynamic stability or instability. So for the rest of this lesson, we're going to talk about why the thioester bond that coenzyme A forms with acyl groups is thermodynamically unstable. The thermodynamic instability of the thioester bond formed by coenzyme A is driven by the presence of sulfur in the CoA molecule. Shown on the screen is a portion of the periodic table showing the major elements apart from hydrogen that are present in the molecules in our body. Carbon, nitrogen, and oxygen are all in row 2. Phosphorus and sulfur are also prevalent in our molecules and are in row 3. Now, as you go up in atomic number, 5, 6, 7, 8, the atoms are getting larger. But the different rows signify the number of electron shells that they have. So hydrogen, which is not shown here, would be in row 1, and it has 1 electron shell. That first electron shell can fit 2 electrons. Carbon, nitrogen, and oxygen are all in row 2, and they have 2 electron shells. The first can fit 2 electrons, the second can fit 8. So at the end of row 2, we have neon, which is not a major component of the molecules in our body, and it has 2 electrons in its first shell, and the other 8, making 10, are in its second shell. If you only have 2 shells, the second shell is your outer shell. Your outer shell is your valence shell. So neon, which belongs to the noble gases, is noble because it's stoic and it doesn't react because its valence shell is full. By contrast, if you don't have a full valence shell, you're going to want to form chemical bonds, and that's characteristic of carbon, nitrogen, and oxygen. So all of these atoms will have 2 electron shells. Their second shell is their valence shell, and the number of electrons missing from the valence shell is going to determine their chemical bonding behavior. Now, phosphorus and sulfur are in row 3. They have 3 electron shells. The third electron shell doesn't fit 8, it fits 18. And so their second electron shell is irrelevant. It's the third shell that fits 18 electrons that's going to determine their chemical bonding behavior. And as you go from the first shell to the second shell to the third shell, you're talking about electrons that are further and further away from the nucleus. And the reason that that's important is because, as we'll see shortly, if carbon's going to form a bond with something else in the second row, the electrons that they're sharing are going to be relatively well aligned with one another. And that is not true necessarily if carbon's forming bonds with things in the third row where the electrons are in a different position relative to the nucleus. In the second and third row elements that are of concern to us in this discussion, the outer electrons of the valence shell that would be shared in a covalent bond take the configuration of what's called a p orbital. And the p orbital is primarily reflecting the configuration on the screen, where a pair of electrons could be present anywhere towards the top or bottom of this p orbital. And they're going to be highest towards the end of the orbital. That's where their probability of being found would be highest on either side. And one pair of electrons can occupy this orbital. Now, there are 3 p orbitals in the valence shell of a second row element. And so one is going to occupy the vertical axis, one is going to occupy the horizontal axis, and one is going to occupy the depth axis. And what's shown on the screen is not a double bond itself, but is the second bond of a double bond. For carbon and oxygen, they would share the first bond straight across from one another. And if they're going to share a second bond, then they're going to have to do it with the vertical axis orbital. And that's going to interact in a parallel manner instead of direct and head-on. And because these p orbitals are in the second shell for carbon and oxygen, they're called 2p orbitals. And the electrons of carbon's 2p orbital are going to be relatively similar in position to the electrons of oxygen's 2p orbital. And that's going to allow them to be relatively well aligned during the second bond of a double bond. By contrast, carbon and sulfur would share their first bond straight across from one another along the horizontal axis. But like carbon and oxygen, they're also going to share their second bond in a double bond through the vertical axis that's parallel to one another. But for carbon, this p orbital is in the second electron shell. For sulfur, it's in the third electron shell, so it's called a 3p orbital. And these electrons are most likely to be found up here and down here, so they're not well aligned with those of carbon. Imagine if you were shaking hands with someone else. And you can imagine that you're lean and the other person's very large, or you're very large and the other person's lean. Well, if you're shaking one hand and you're delivering that hand straight across, then it's going to be relatively easy to form a tight connection. If you were shaking two hands with someone and you were of equal size and your two hands were well aligned, you could form a pretty strong connection. But if you're trying to shake two hands at once and one person's 3 times as big as you are and you're stretching out like this, it's going to be really hard to get a strong connection that way. And that's what's happening with carbon and sulfur. When they form a double bond, it's not that stable. So let's now define a thioester bond and look at how the unstable pattern of double bonding between carbon and sulfur impacts its thermodynamic stability. A thioester is the sulfur-containing analog of an ester. An ester is shown at the top. If we have a carboxylic acid and we have an alcohol, the OH comes off the carboxyl group, the H comes off the alcohol group, and it forms water. Through dehydration synthesis, we make an ester, which has the pattern of a carbonyl bound to an oxygen bound to some rest of the carbon-containing molecule. If we have a carboxylic acid instead bind to a thiol, which is the sulfur-containing analog of an alcohol, and is called a thiol because thi comes from the Greek theon for sulfur and ol refers to an alcohol. If we have the same exact reaction with a thiol, we'll produce a thioester, which has a carbonyl next to a sulfur instead of oxygen, along with the carbon that adjoins it to the rest of the molecule. Ester bonds are stabilized by a principle called resonance. Resonance is the delocalization of electrons, and the resonance stabilization of an ester is shown at the top of the screen. The predominant configuration of the ester that we just went over in the last slide is shown on the left. The ester can also exist in the configuration on the right, and that's a resonance form. To see what's happening more clearly, the electrons that are moving around are color-coded so that on the left, the dark green lone pair on the bottom oxygen corresponds on the right to the dark green bond between the carbon and the bottom oxygen, and the light green bond on the left corresponds to the light green lone pair on the top oxygen on the right. What happens is that the lone pair on the bottom oxygen can move into the position of a double bond with the carbon. If that happens, carbon can't have 5 bonds, so the bond that it shares with the top oxygen will move up as a lone pair on that top oxygen. The electrons moving from the bottom oxygen in the direction of the top oxygen create a negative charge on the top oxygen and a positive charge on the bottom oxygen. The form on the left is more predominant than the form on the right because there's no separation of charge on the left and there is on the right. Remember that opposite charges are attracted to one another, so forms are higher in energy when there's more separation of charge. Nevertheless, that's talking about the relative stability of the two resonance forms. The fact that we have two different alternative configurations makes the molecule as a whole stronger together. The reason is each configuration has its own vulnerability. We know that double bonds represent an electron-deficient state. That's vulnerable to reduction, to the addition of electrons from other molecules. Negative charges are attracted to positive charges. This is vulnerable to an interaction and reaction with something that's positively charged. Vice versa for negative charges down here. Because they each have their own vulnerability, the ability to switch back and forth whenever that vulnerability becomes relevant is going to save them from engaging in potential chemical reactions and make them more stable. Now, it's important to note that to think about them as alternative configurations is actually wrong. It's a mental tool that we're imposing on the truth. The truth is that the electrons are delocalized across the alternative configurations in a continuous manner. And it's really just a matter of probability that we find them in one position versus another. The reason that we present them as alternative configurations is because it's much easier to think about, but always keep in mind that it's just a mental tool to do so. Now, the resonance stabilization of an ester is shown on the top. The analogous resonance stabilization of a thioester is shown on the bottom. And indeed, this resonance stabilization exists. However, we talked before about how the fact that a double bond between carbon and sulfur is much less stable than the double bond between carbon and oxygen, because carbon is binding its 2p orbital electrons that are relatively more close to the carbon nucleus, with the 3p orbital electrons that are relatively further away from the nucleus of the sulfur. And because they're not aligned well, this bond is much weaker than the double bond between carbon and oxygen. Because the resonance form is so weak, the thioester bond is poorly resonance stabilized. Compared to an ester bond, it's thermodynamically much less stable. That means that breaking that bond has a larger negative delta G. And because it's thermodynamically unstable, despite the fact that it, like all the other major metabolites in human metabolism, is kinetically stable, makes it highly useful to enzymatic metabolism because the kinetic stability makes it easily controlled by enzymes, and the thermodynamic instability of the thioester bond gives it a high payoff when broken. During the alpha-ketoglutarate dehydrogenase reaction, when we succinylate coenzyme A, we're storing energy in the thioester bond that is then used to synthesize ATP in what's called substrate-level phosphorylation. It's called substrate level because succinate and succinyl CoA are substrates in the TCA cycle reactions, and we're synthesizing ATP there in a rather unusual manner compared to most ATP, which is produced in the electron transport chain with energy taken from the substrates of the citric acid cycle away carried by NADH. Here, the substrates of the citric acid cycle directly invest energy in the phosphorylation of ADP. Succinyl CoA has its thioester bond broken. That energy joins phosphate to ADP to produce ATP, leaving behind succinate and free CoA. This enzyme is called succinyl CoA synthetase, which seems a bit odd right now because it's not synthesizing succinyl CoA, it's synthesizing succinate. But we'll see in the next slide why it bears that name. A lot of biochemistry texts will take succinyl CoA synthetase as it exists in E. coli and describe it. But in humans, it works differently, and in us, it works similar to other mammals. In E. coli, the enzyme uses ATP or GTP. In mammals, there are two different isozymes, meaning variants of the same enzyme, that predominate in different tissues according to their needs. In skeletal muscle and heart, where the needs for energy are highest, succinyl CoA forms succinate in the manner we just described. But in the liver and bone marrow, where there's a lot of synthesis of heme, it's important to maintain succinyl CoA in very high concentrations, because as we described in the last lesson, succinyl CoA is used for the synthesis of heme. Therefore, a different isozyme predominates in liver and bone marrow that works in the opposite direction and utilizes energy from GTP instead of using ATP. GTP is guanosine triphosphate, whereas ATP is adenosine triphosphate. GTP and ATP are very similar, but guanosine triphosphate uses a different nucleoside. In this version, succinate binds to CoA using the energy in GTP to make succinyl CoA for heme synthesis. In reality, using GTP here is just a way of controlling what enzyme is most active. The energy in GTP is equilibrated with the energy in ATP by the enzyme nucleoside diphosphokinase. If we have a lot of GTP and a lot of ADP, and we need more ATP, we will simply take the energy from GTP, invest it in ADP to phosphorylate it to ATP, and vice versa. So what we're doing in liver and bone marrow is ultimately using the energy from ATP to, through the enzyme nucleoside diphosphokinase, provide the GTP necessary to make the GTP-specific form of the enzyme go forward to provide the succinyl CoA necessary for heme synthesis. One way to look at the significance of capturing energy in the thioester bond of coenzyme A during the formation of succinyl CoA is to look at the delta Gs of the various relevant reactions. And when we look at the delta Gs on the screen, we have delta G naught prime. The naught, symbolized by the degree symbol, means delta G standard. And the significance of delta G standard is that we're assuming equal concentrations of all of the relevant reactants. And we assume that they are 1 molar. Molar is a unit of the number of molecules. In reality, we don't have equal concentrations, and the concentrations aren't 1 molar. We do this as a way of giving an objective number to a single reaction whose true delta G will vary depending on the concentrations of the reactants. But we can't describe a moving target with a single number, so we use delta G standard to control for the concentrations of reactants. In addition, chemists will use standard conditions that are not at the pH that we find within the human body and within other living cells. And so the prime, symbolized by the apostrophe-like symbol at the end, refers to a pH of 7, which is approximately the pH that we would find in our cells. The delta G naught prime of the various reactions is shown on the screen here. If we look at the delta G of succinyl CoA hydrolysis, it's negative 33.5 kilojoules per mole. Kilojoules a unit of energy. Again, molar is a unit referring to the number of molecules. So negative 33.5 is the energy contained in the thioester bond between succinyl group and coenzyme A. The energy of the terminal phosphate bond of ATP can be described for the energy of ATP hydrolysis, which is negative 30.5 kilojoules per mole. We see right there that there's a little bit more energy in the thioester bond of succinyl CoA than there is in the terminal phosphate bond of ATP. And that means that we capture just enough energy in producing succinyl CoA that we could then use to invest in ATP. Another way to look at this is in the net delta Gs for the reactions of isocitrate dehydrogenase, which did not produce an acyl CoA during its decarboxylation reaction, versus the net delta G of alpha-ketoglutarate dehydrogenase, which did. The net delta G for isocitrate dehydrogenase, meaning the energy left over after doing everything that isocitrate dehydrogenase did, is negative 8.4 kilojoules per mole. After everything in alpha-ketoglutarate dehydrogenase is done, the energy left over is negative 30 kilojoules per mole. That's negative 30 kilojoules per mole that's left over after we produce succinyl CoA. So had we not produced succinyl CoA and stored the energy in the thioester bond, we would have released more than 60 kilojoules per mole. Now, the large negative delta G of this net reaction helps make it incredibly energetically favorable and helps provide an enormous amount of direction in favor of the products that makes that reaction essentially irreversible. In fact, the delta G that's negative for isocitrate dehydrogenase essentially does the same thing for that enzyme as well. So this large negative delta G is more than enough to provide directionality for that reaction. And that means that if we had released twice as much energy, we would have been wasting it because we released enough. We want to save what we can save to make ATP. So if we think back to the enzyme and how it worked, one of the reasons that it was so complicated with the flexible arm of the lipoic acid moiety of enzyme 2 reaching in to grab what would ultimately become the succinyl group and take it down into its own active site to succinylate CoA, a large part of what's going on there is if we hadn't done these things deep in the pocket of an active site designed to provide the right context to facilitate those reactions, we would have wasted the energy because there would be no way to capture it as ATP if we weren't reaching into one enzyme that specialized in producing the succinyl group and then reaching deep into a different active site that was optimized to succinylate CoA. So this is the energy part of the story, and the moral of this story is that coenzyme A is needed to capture energy. We'll see many other examples of this as we go along. But that's not the whole story about succinyl CoA. In fact, we don't just invest energy in the thioester bond and then into the ATP molecule so that we use it as ATP. That's one nice thing about it. But it also turns out that we're making an exchange with phosphate in that reaction. Phosphate has something very valuable that we would not be able to get had we not taken energy in the thioester bond and given it to the phosphate so it can go away happy with ATP. What is it giving us? Well, you can find that out in the next lesson. The audio of this lesson was generously enhanced and post-processed by Bob Devodian of Torian Mixing, giving you strong sound and dependable quality. You can find more of his work at torianonlinemixing.com. To continue watching these lessons, you can find them on my YouTube at youtube.com/chrismasterjohn or on my Facebook at facebook.com/chrismasterjohn. Or you can sign up for MWM Pro to get early access to content, enhanced keyword searching, self-pacing tools, downloadable audio, downloadable transcripts in PDF form, web page transcripts, a rich array of hyperlinked further reading material in the transcripts, and a community with a forum for each lesson. If you really want to own these lessons, study them, and get the most out of them, you can sign up for MWM Pro at chrismasterjohnphd.com/pro. All right, I hope you found this useful. Signing off, this is Chris Masterjohn of chrismasterjohnphd.com. You've been watching Masterclass with Masterjohn, and I will see you in the next lesson.